Hello everybody. So consider the following problem. We are given a 3 by 3 square grid with those 9 squares, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we would like to figure out how many different coloring patterns are there where we use 2 red, 3 white, and 4 times the blue colors. So when we say coloring patterns, what we really mean is that we recognize that this shape has a certain symmetry, and we would like to consider two colorings which can be obtained from each other by a simple rotation or a reflection as the same coloring. So we don't want to overcount this thing, right? So just as an example, so for instance, red, red, white, 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 and then blue, 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 blue is the same as the following one: red, red, blue, white, 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 and then blue, 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 blue. Why? Because we can simply obtain this second one from the first one by simply taking a 90-degree rotation clockwise. Clockwise rotation. So as a result, we want to make sure such overcounts will not happen. If the grid was fixed, or for instance, if the squares were labeled like this, then life would have been extremely simple, right? So the answer would have been 9 factorial divided by 2 factorial, 3 factorial, and 4 factorial, and that would be the end of the story. But that's not the case, right? For this problem, we are told that, because of those symmetries involved, we want to really, in the end, find out just the patterns and the situations where you can obtain, for instance, once you count this, you don't want to count this one as well, right? So because this thing already covers it, it's the same pattern. All that happens is just a rotation. So what are all the symmetries involved in a square? I think we described it earlier. So let me just remind you, if you have a square, the square has in total, the shape is a D8. Just to remind you, it's called as D8, dihedral group, and the 8 symmetries are basically 4 rotations, and 4 reflections. So the 4 rotations are, as you can imagine, a 90-degree rotation, 180-degree, 270-degree, and then 360-degree rotation. But because the 360-degree rotation leaves the object unchanged, usually we call this as the identity. So if you guys want, let me just put these underneath it. And so the rotations are the identity. We can call it I4, for instance. The 90-degree rotation, the 180-degree, and then the 270-degree rotations. For the reflections, we have 4 types of reflections. I call the horizontal reflection across this axis as P, a reflection across this axis as Q, and then we can have a reflection across this diagonal or this one, R and S. That's it. So in total, we have 8 symmetries. So when we do all the work, we need to respect those symmetries, and so that we should keep that in mind. All right. So it turns out for this problem, just using a standard Burnside lemma won't work. You can't just say, oh, this is just Burnside with 3 colors. No, not really, because the colors are not in unlimited supply. We have a limited supply of red, white, and blue colors. And because we want to use exactly that, this is a special case of Burnside's lemma, something called Polya theorem. That theorem solves this problem pretty neatly, actually. But what I want to do first is to solve this just using casework. Because the cases are going to be, some of the cases are, they are so symmetric. For those cases, I think for 2 of the cases, I will be using Burnside's lemma. But for other cases, I will just use standard counting tricks. And so yeah, so hopefully that should work. So what I want from you is, if you want, at this point, just pause the video. Why? Because I mean, we are all stuck at home nowadays, and so we want to keep ourselves busy. I think this problem is really nice in terms of keeping busy. So today I think I spent about 45 minutes, because at one point I messed up my calculation. It kept giving me the wrong answer, and then eventually I was able to figure where I messed up. But yeah, so it's a pretty good way to spend a day. So if you are at home and pretty much nothing better to do, if you don't have that much time today, probably it should take you, this question will probably, the casework will take you about 45 minutes to an hour. If not, then just wait till the weekend and then start working on this problem. All right, so I am assuming now that you did pause the video already, and so here we go. So what I will do is, well, what are all the cases, right? So I will do a casework based on the distribution of the 2 R's. So we have R and R, right? So what are all the cases involving the locations of R and R? And for the time, from now on, I won't even bother drawing an actual full square. Why don't I just do it like this, right? The game tic-tac-toe. So what are all the potential positions for the 2 R's? And again, if you want, you can pause the video. But I found out exactly 8 such positions. Can you see them? Again, anytime, just pause the video. All right, so what are they? Essentially different positions. There's only 8 of them. All the other positions for R, normally you might say, hey, this is just 9 choose 2 ways. That's not true, because like I said, so for instance, R and R, these 2 positions are exactly the same. Why? Because I can simply obtain this position from this one using simple rotation, for instance, right? So similarly, this is not that position is also not allowed, because I can simply obtain this second position from the first one by just simply a reflection across the diagonal R. The diagonal R is this one. So yeah, so I want to find out the essentially different positions where I can place the 2 R's, and here they go, like that. Then we can have, for instance, this one. First, I started by putting all the ones where one of the R's is in the corner. I want to first make sure that I exhaust all those cases. I think that's another case. This is another case. And I don't think there's any other distinct case where there's an R in the corner. Now the others won't have R in the corner. So first I want to handle the cases where R is not in the, well, actually let me show you. So I got this one, and then in the other one I have that, and finally I have this. I don't think there is any other way the 2 R's can be distributed. Now the rest of the problem is just yeah, so just counting each and every single one of them. So we have, let's start with the first case, right? So case 1. So this is case 2 and so on. Case 3, 4, 5, 6, 7. Yeah, that should be an easy exercise. So before each case, if you didn't want pause the video so far, try to count how many distinguishable ways you can place the 3 what was that, the 3 white and the 4 blue. So we have 7 spots in total, 1 2 3 4 5 6 7, and we need to put in those spots 3 white and 4 blue. Okay, so let's do it step by step. Maybe the initial ones I can do it if I do it a bit higher. Okay, there you go. All right, so let's do the initial one here. So we have 2 R's here, and we have 8 spots. Well, the first thing I recognize is that there is no way I can put the 3 white and the 4 blue in a symmetric ways in the remaining 7 spots, meaning I can never have a situation where I will overcount, right? So those patterns with 3 white and 4 blue, when the R's are in this position, right? So we are in case 1. So because of that, this case is the easiest of them. 7 spots, we need to choose which 3 will be the white squares, and boom. So we are done in this one. So 7 choose 3, 7 times 6 times 5, divided by 3 times 2 times 1, which is just 35. That's it. Wow, you might say, hey, that was easy. Okay, so this case came out 35 ways. Okay, so that's the answer for that first case. Well, is there any other case where there are no symmetries involved? Yes, there's one more case where there are no symmetries involved, and it is this case over here. You can just quickly check that there's no way that once I have a coloring or a pattern, whatever you call it, there's no way that after rotating or reflecting it that I will get back a similar coloring. So therefore this one is also 35. All right, so we already finished counting 2 of the cases. All right, now let's go to case 2, back on track. So case 2, like I said, I will, as much as possible, I will try to avoid using Burnside's lemma, but sometimes the casework might be a little bit tricky. So in those, actual 2 of the cases are tricky. So for those, I will just use Burnside lemma because I don't want to make a mistake. Burnside lemma is a guaranteed way to give you the correct answer. So quick case number 2. So we have the case where there's an R here, an R here, and then we have 3 white and 4 blue squares that we need to place in those remaining 7 spots. How can we count? Well, it turns out that some of the arrangements are symmetric, so you want to make sure you do not double count them, right? So we want to ignore those symmetric cases. We want to count them exactly once. Everything else, we will just figure that because the shape is symmetric across this diagonal over here, there is a symmetry applying here, and this is the symmetry R. Everything will be counted twice, basically. We are double counting everything, except it turns out there is 3 positions where, because it is symmetric, we need to make sure we are just counting them once. All right. So the unadjusted count was 35, but because everything is counted double, I'm technically supposed to divide that 35 by 2, but obviously 35 is not divisible by 2. So that tells us already that, hey, maybe some of the cases, it's just unique. It's no double counting, right? Does everyone agree? For instance, if I put, let's say, white here, and white here, and then everything else is blue, well, this, okay, so let's put the blues here. This technically is the same thing as this one, red, and then I could have as well put the whites here, and then the blues in those remaining spots. Hey, these 2 are exactly the same thing. I can just take the first picture and then reflect it across this diagonal, and boom, I would have gotten the same thing. So I don't want to double count these type of situations, right? Well, okay, so then first let's figure how many, let's just get rid of all this. How many situations are unique? They are not double. And it's kind of, I think, easy because we have 3 white. The whites, one of the whites definitely has to be here. Actually, let me just put those colors back because they are red. So maybe I should put the red color here, right? So red. Okay, there you go. Okay, one of the whites should be here. Then I realized that these 2 squares are symmetric. These 2 squares are symmetric, and then these 2 squares are symmetric. So in total, I need to choose one of those 3 shapes, basically, right? So either I have one of the whites here, and then the other 2 whites on the place where the triangles are, and the remaining spots are blue, and so on. Because this is symmetric, this will definitely be counted once, even if I reflect it across R. Do you guys agree? So there are 3 cases, so subtract 3. So 32 left. Pretty much for all the remaining 32 ways, each one will be double counted, just like the example I gave just a minute ago before this picture, right? So I will just go ahead and divide this by 2, 16, and add back those 3 cases where I'm counting only once. So each of these 16 are counted twice, and then we have 3 which look like this. So yeah, I'm pretty happy. So 16 plus 3 is 9 ways. Yay. Alright, so that's pretty straightforward then. So this one is, 19 ways. What am I doing? 19 ways. Alright. Okay, so we're done with the second case. The third case turns out to be a little bit monster. The reason is because there is 4 symmetries. What are the 4 symmetries applying to the third case? Well, this shape is symmetric with respect to this diagonal, with respect to that diagonal. Obviously, we still have the identity, but at the same time, it's also symmetric with respect to a 180-degree rotation as well. So 180-degree rotation, R and S, and I might as well just call the I as well here in this picture. On the previous case, the 2 symmetries were I and the R diagonal, right? In the first one, it was only I. There was no other symmetry. Awesome. So because of that, I'll just leave it to the end. All right. So I don't want to attack this one right now. Okay. So number 4 is easy as well. The number of symmetries are slightly different, but still it is decidedly easy. So the only symmetries here are I and this axis of symmetry across this, which we called it as Q. Right? There's no other way we can have. So like I did earlier, so number 4, let's just draw the picture again, and yeah, so R here, R, oh sorry, we decided to skip that case, the 4th case here, this one. So we have an axis of symmetry here. Well, again, so what are the patterns which will be counted once, and what are the ones which are basically double counting, right? So for instance, things like this will be counted twice: white, 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 and everything else blue. Why? Because you can reflect it across, and then this is the same thing as this one, red, and then white, 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 right? So because these two are easily obtainable from each other. These 2 patterns are exactly the same. I don't want to over. So in the end, I'm technically supposed to divide 35 by 2 again. But again, after I first figure how many symmetries, just like in the previous picture, we had 3 of them which were symmetric. So how many shapes are symmetric when there are 2 R's as such, and when the axis of symmetry is Q? Alright, so this is the axis of symmetry here. Well, you can easily check that there are really 2 cases. Either the 3 whites are like that, after which all the other blues are here. That's one way. 1 plus. So I'm counting the symmetric ones, right? So the let me just do it on this side. Symmetrics. We have so far 1 plus, or there's only 1 white along this like middle column, and then the other 2 whites are on the 2 sides like that, or if that white is over there, the other 2 whites are like this. So in a sense, I'm really doing the following. If you label these as A, B, C, D, D, and E, E, right? So either the first white is in A, after which I can choose either D's or the E's, so 2 cases, or the first white is in B, after which we have the D's and an E's, 2 ways, or one of the whites is in C, A and B doesn't have a white, and either I choose the D or the E. So therefore, do you guys see that this is 3 times 2? So that's 7 symmetries. So I make the same adjustment, 35 minus 7, that's 28. Divide 28 by 2, that is 14, and add back the 7. So this is 21 ways. That's it. Oh, that was easy. 21 we said, right? So let me use the same color, green. What did we say? So let me write it here. 21. Okay, so but by now you guys already see where I'm going with this. So we already counted, so far we have counted case 1 is done, case 2 is done, case 4 is done, case 5 is done. We still have 4 more cases, so let's keep going. uh, okay, so like I said, this is a good pastime activity, I guess. We can do this one. I think 6, 7 are equally hard. It turns out that the two hardest cases are these two cases, 3 and 8. So make sure you work on 3 and 8. The reason 8 is also hard is because 8 is also have 4 symmetries like this. So it has the P, I mean the Q. It has the P as well, and then it has the what? The 180 degree thing, 180 degrees, and then the identity. So in total 4, 1, 2, 3, and 4 symmetries there. So I'm a kind of, okay, let's just leave those two cases to the end because they are kind of annoying. Okay, so let's do number 6 then. So in the case of number 6, again, let's count how many shapes are symmetric. Well, the symmetry will be okay, either, I think it's the same thing, right? First, the axis of symmetry here. What is the axis of symmetry? Just this one, right? So the only symmetries applying here are I, and we call this one as R. So either the 3 whites are here. That's one way symmetry can happen. So on the main diagonal, R, you can have 3 whites. So that's 1 plus. So these are, I'm counting how many of the patterns are totally symmetric. Or, with respect to R, or 1 white is over there on the main diagonal. There is no white here, so meaning blue and blue on the other 2 places for the main diagonal. And then the whites are symmetric with respect to R, with respect to that main diagonal. Either it's like this, or I could have put them over here. So 2 choices for if white is over here. But then white can be anywhere along the main diagonal, right? So white could have as well been here as well. Again, 2 choices, either here or here. And these 2 are blue now. 2 choices there. And then similarly, white is here. And then again, A or B's, one of them is both whites. So 3 times 2, that's 7 symmetries again. Okay, pretty much the same accounting. So 35 minus 7, because each one of them will be just counted once, right? So this is just 28. 28 over 2, that is 14, and finally add 7 to, oops, add 7 to it, so 14 plus 7, that's 21. Whew. All right, so this was nice. So that's 21. Where can I write? Over here. So that's 21. So we are pretty good on that one as well. Okay, lastly, number 7, last easy case. So the only symmetry on this one is this one, the Q symmetry, and I, obviously. I is always there, right? So this one had only I. All right, so I and Q symmetry. Well, again, we want to place 3 whites. Let's first count the symmetries. So the white is, well, in this case, it is slightly different. So you have to have a white here for sure. And then you choose 2 more whites. Well, either they are here, 1, or they are here, 2, or they are here, 3. There's really 3 symmetries. So 35 minus 3 is 32. Each of the other colorings has 2, like, 2 ways to place them. So kind of, double counting for each of the remaining cases, and then add back the 3. So that's 19 ways. Yay! All right, so case 7 has 19 ways. All right, there you go. Maybe I should have kind of colored them in a different way, right? So I'm not happy with the way I colored them. So 35, 35, 19, 21, 19, 21. All right, so we are now finally to the remaining 2 cases, case 3 and case 8. I counted these cases like one by one. It was so annoying, and so I don't know. So I mean, you guys should definitely watch my Burnside lemma series if you want. You don't have to watch the proof. So you can just skip. I think there's 3 back-to-back proof steps. I mean 3 videos. The first 2 videos, just skip it. The notation, the abstract algebra notation, just skip it. Just go to the 3rd video where it shows you the formula basically. So that's one way. But if you want the whole thing, it will just take you about 30 minutes to gain that skill, which I think is kind of useful, because in the end counting symmetries is a big thing, right? So they count symmetries in biology, in chemistry, in physics, right, in quantum physics, and so many other areas, obviously in math, in different areas of math. We count symmetries as well, so especially in algebra, right? So abstract algebra and group theory. So that's something that's extremely useful. That's actually one of the other videos that I want to share with you, probably. Well, after this one, so this thing is over, we will go over Polya. So I'll solve this same problem in just kind of in 5 to 10 minutes. It's possible to solve it with Polya theorem. So the title to this video is probably misleading. So Polya, you came here to watch what Polya theorem says, but here at least we are working on the cases. But anyhow, after this we have the Polya theorem, and after that I would be quite interested in just exposing you guys to a little bit of abstract algebra, especially group theory. And one of the best exercises that I like a lot is to look at first to understand what is the definition of a group, than the idea of a subgroup. And one of the things that's super useful is to understand what is sim 2, sim 3, the symmetric group of 2, 3, sim 4, sim 5, sim 6, maybe all of them. What are the subgroups? And then we can check the automorphism groups of graphs, which is super cool idea, where you really, all of these pieces, finally you can put together the pieces and you can see the big picture, which is kind of important. From there, the whole thing is, you suddenly realize a lot of results in number theory, especially, for instance, the results about the order of an element and things like that nature, they really follow up directly from group theory, basically, which is really cool. All right, so finally this 3rd case and 4th case. So it's as if we are using a Burnside inside a Burnside, right? So we already know that quite a few like each of these can be shown, like this thing can be reflected, rotated by 90 degrees or reflected and so on. I'm totally like aware of that. So that put aside, because we already ignoring those cases, right? Because all we care is how many different patterns. Okay, so in a sense, but whenever I have 2 R's, the shape is almost fixed, right? So because you have 2 R's, except one of these 4 symmetries can still act on this, and we can end up double counting the patterns, right? So I don't want such a thing to happen. So now finally let's count how many ways this can be happening. So let's go ahead and do it over here. Yeah, so like I said, I did so many mistakes. Like I kept counting this over and over, doing the mistakes. So I don't want to show you the way, like the long way to do it. So Burnside, because does it pretty quickly. So the symmetries acting on this is the I, or I4 you can call it, 180 degrees. And then the 2 diagonals, right? So reflections across the diagonals, that's it. P and Q are not axes of symmetry. They won't keep the shape unchanged like this. All right, so how many ways? Well, 1/4, because only these 4 will act on this, because of that restriction that those 2 R's are the way they are. 7 choose 3 ways are the fix of I. So the fix of 180 degrees, this one is a little bit annoying. Well, okay, so how many colorings will remain fixed after I apply a 180 degree rotation? So yeah, you might want to pause it at here and then try to double check. But okay, so assuming you guys pause it, either I can place the 3 whites over here. After a 180 degree rotation, they will come back to here, and obviously the rest is blue. Or the 3 whites are here. Again, after a 180 degree rotation, they will be back here. Or the 3 whites are here, right? You guys agree? So there's really 3 ways. Plus, all right, so we are done with the 180 degrees. Next, R. R is this diagonal over here. This one. All right, so how many, what is the fix of R? How many colorings will remain fixed after I apply this reflection across this diagonal R? Well, okay, so where should I put the 3 whites, right? So let me see. Well, obviously one of the whites has got to be at the center. Now the rest is I can go ahead and label them. For instance, whatever color is one of them, the other one should be the same color, BB and CC. So I think you guys would agree that there's really 3 ways to do it, right? So I pick one of the doubles, one of the pairs of either A's, the B's, or the C's, and I place the whites there, and boom, right? All right, so 3 ways there. And finally, S. You might think, hey, S is 3 as well, and that was one of the mistakes I did early on. That sucks, so you should be doing it with delicacy, so be careful when you do it. So the other diagonal now. So check this out, so be careful on this one. So for the other diagonal, again, it seems there's a white here. Well, okay, so that's not necessarily the case. So there are 2 sub cases here. Either we have 3 whites over here. Now I'm checking the symmetries across this axis, right? Across this axis over here. So either I have 3 whites here, after which I put the blues. So there's one way there. Plus, or there's really one white in the main, in that diagonal, in this diagonal, the 45-degree line, which is S. There's only one white, which means either I have a white here or here, right? 2 choices. So you guys, either I have a pair of whites here or a pair of whites here, and everything else is a blue. Do you guys agree? So there's really 2 choices when white is here, or white could have been here, and then again 2 choices, either A or B, or white could have been here, again 2 choices. The first white is here, and then the other 2 are, okay, so really 3 times 2, and that's it. So if you add these things up, divide by 4, if I'm not mistaken, that is 35 plus 3 plus 3 plus 7, not 3. 3 plus 3 plus 7, okay, 13, right? So that's 48, that's a 12. All right, so we did that one as well. Yes, so this case is a 12. Let us write it right here. So this case is a 12. Yeah, let's just write over here. And let's highlight it like we did earlier. There you go. And finally, this last case, which is pretty much the same thing, right? So by now we can easily do this case as well. Let us do it somewhere here in that corner. So we have the 2 R's. I'll do something fun. So after we are done the counting, because we are over time anyways, I'll show you my struggle basically, how I messed up. So the 180 degree, the P and the Q, right? So let's place the whites now. Okay, well, let's apply Burnside 1/4. So because we have 4 symmetries, so I is pretty much 7 choose 2, 7 choose 3 again. The 180 degree, after a 180 degree rotation, this guy will go over here. That guy will be mapped to there, this guy is there, and then the one at the center will remain. So which means, because I have 3 whites, so one of them is definitely at the center, right? And then I can choose, I have 3 other spots. Either I can put the 2 whites, remaining 2 whites on the spots of the A's, or I can put them over here, or I can put them over here. I have really 3 choices plus. All right, so we did that one. So next is the P case. So P case was the horizontal reflection across the horizontal axis. Again, our shape is symmetric because the way the R's are. Okay, so reflection across this axis. Again, 2 cases. Either the whites, all 3 whites are here, one way plus, or there's only 1 white on the main diagonal like this, and then the other 2 whites are either here or here. 2 choices again. Do you guys see that? So again, 3 times 2 here, 3 times 2. Because white can be here, and then 2 blues next to it. Here and here 2 blues, and then either I choose these 2 A's or these 2 A's, and so on. All right, plus, okay, finally we have the Q. All right, so this is a little bit annoying for maybe, huh? So there is the Q. Well, definitely this one is a white, and now we have two choices: AA, BB, CC. Sorry, three choices. That's it. So that's 1/4. 35 plus 3 plus 7 plus 3, which is, just like in the previous case, 10, 13, 48, 12 again. Okay, so finally we are done with this problem, right? So 12 here. And finally, let's also go ahead and yeah, you just add these things. So we have two 35s. Let's use black color here. Those two are 35, so that would make a total of 70. Then we have how many 21s? These two are 21s, so that would make a 42. And then we have 12s, two 12s. That's a 24. And then two 19s. That's a 38. Well, 38 plus 42 is 80. 80 plus 70 is 150. 150 plus 24 is 174. Going back, there's really the answer. Let's write it here. Answer 174 coloring patterns, right? So patterns would have 2 red, 3 white, and 4 blue, up to rotation and reflection. So that's it. Okay, just for those of you who are not convinced, I'll just show you the case, especially these cases 3 and 8. I mean 3 and 8, yes, those two cases were a little bit messed up. So let me show you the 12 ways. I claim that there's no other ways. Let me find out every single one of the 12, and then let's see if they add up to 35, right? So each one are different. We know that technically they are supposed to be 35, but there's double counting. So let's go ahead, and so that's kind of for fun I'm doing this. So if you are if you would like to stop here and then go to the second video, hopefully, that I will shoot in a few days. okay, promise I will do it in probably 1 or 2 days. Yeah. Anyhow, so we have the grid. Okay, so we said that there's 2 red here, and already I know that there is the answer here in this case is there's the 2 red. How many cases are there? Because the solution is 12, I should have 12 cases. Okay, so you can fast forward the video at this step if you want. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'll show you how Burnside makes our life so much easier. If you didn't know about Burnside, you would have had to create all of these, which is such a mess. I mean, it took me a long time to figure out what are the 12 cases, and I kept making an error. So that's why I think it was reasonable to use Burnside for the cases 3 and 8. All right, so well, we could have had white like that. Oh, actually, let me put the whites in a different color. Why don't we put the whites in the green color? Oh no, blue color. Blue is better. Oh, actually, gray is better. Okay, white. We could have it like this. How many ways can this happen? Well, remember that because I'm just doing it for the last case. This is case 8. In case 8, the symmetries were P, Q, QP, I, and 180 degrees. The horizontal, the vertical, and then the 180 degree rotation. So what other shapes can be obtained using this shape? Well, pretty much the only other shape you can obtain is if you rotate this 180 degrees, or if you take a reflection across P, across this this axis of symmetry, you could have gotten this as well, which technically they are the same pattern, right? So as a result, this one has 2 ways. You guys see that? I'll show that this adds up to 35 as suspected. All right, so a second case, for instance, would be white like that. And if you rotate it 180 degrees, the whites will be aligned like this. Again, this one has 2 ways. The next one would be, I can put the whites here. This one has only 1 way. That's it. if you rotate 180 degrees, it will be back to here. If you reflect across this axis, it's back to here. If you reflect across this axis, it's back to here. If you apply the identity, it's still the same thing. There is only one way. Well, next one is I can put the 3 whites over here. And after reflecting across this, the 3 whites will appear here. So there's really 2 ways for this case. Next case I can think of, let's do a case where there's 4. This one has 4 different ways, right? So, oh gosh, there's so many. Okay, let me put it over there. Do you guys agree that, so the reds are here, right? So that one, so is 1. Or if I reflect it across the horizontal axis, it becomes like that. Or if I rotate it 180 degrees like that, or if I reflect it across Q, it will end up like that. So do you guys see that it is really 4? So we have 4 in this case. Next is, for instance, white, white, white. I hope I'm not overcounting anything here. That would be a horrible turn of events. Horrible. 2 ways here. Why? Because you can reflect across Q. For the next one, I got W, W, W. And this one is also 4. You can easily check it yourself. That, well, okay, so test it yourself. You will easily see it. Next is W, W, and then another W on this side. Again, this one is a 4. Then we can have, I think, W, W, and then a W here. This one is also 4 ways. We could have W, W, W like that. 2 ways only, actually, for this one. It's the other way is like this, putting the 3 W's over here, basically. What am I missing? Yes, so I'm also having W, W, W. I hope I didn't count it yet. And this one is 4 ways. And finally, W, 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 4 ways for this one too. That's it. This accounts for hopefully 35 of them, right? So 1, 2, 3, 4, 5, 6, 6 times 4. Plus how many 2's? 1, 2, 3, 4, 5 2's. And how many 1's? 1. Just 1, 1. 1, 1. 24 plus 10 plus 1. That's indeed 35. Okay, in a similar way, if you guys want, you can lay out all the different, how many ways? 12 ways for this one and so on. So every single one of them is possible to do. But you guys probably have better things to do. But yeah. Alright, so that solves this problem. So in the next video, probably I will shoot it tomorrow or in 2 days, hopefully before the weekend. I'll show you how you guys can solve this problem in about 5 to 10 minutes. Using Polya theorem, which basically converts this problem into what? Into an algebra problem using binomial expansion, basically. Thank you.